Good morning, students. Welcome back to our physics classes. So, we have finished up our syllabus, the whole syllabus we have finished, and here we have to start with our revision classes. So, this is the first revision class in which we are going to revise the concept of superposition of waves. Superposition of waves. And this superposition of waves, in your textbook it is given in 3 different chapters, but here we are going to revise the chapter as a single concept, that is superposition of waves. And while going through the classes, we have already seen that the superposition of waves, even though it is given in 3 different chapters, the concept is same. So we are all together revising all those 3 chapters. All those 3 chapters means all are single leaf chapters, have 2 or 3 concepts are only there. So already I told you all these are coming under one caption, that is superposition. So we are going to start with the superposition principle, superposition of waves. So this superposition of waves, the first topic or the first concept that you have to learn or remember is superposition principle of superposition. So as I already told you, this is the vector sum. That means when 2 waves are superposing simultaneously, then the resultant displacement will be the displacements generated by individual waves irrespective of the presence of the other. That means y is equal to y1 plus y2. That is, we are generally used for the description altogether. So that is the superposition principle. The individual displacement they can make, the waves can make their own individual displacements, and the net displacement will be the vector sum of these individual displacements. So that is the superposition principle. Based on superposition principle, we have already defined interference of 2 waves. Interference of 2 waves. See, there we have considered, there we found y1 is equal to a sin omega t minus kx is the incident wave, one wave, and y2 is equal to a2 sin omega t minus kx plus phi, the second wave. According to the superposition principle, y1 plus y2 is equal to y. Then you go through that y1 plus y2, and using the trigonometric identities there, then you are getting a1 plus a2 cos phi is equal to r cos theta, then a2 sin phi is equal to r sin theta, then finally you are getting r square is equal to a1 square plus a2 square plus 2a1 a2 cos phi. See that r is the resultant amplitude, and a1 and a2 are the amplitudes generated by the individual waves. So we can have where you are getting the resultant amplitude maximum and where you are getting the resultant amplitude minimum. That is depending upon the value of phi. So when phi is equal to 0, 2 pi, 4 pi, that is even multiple of pi, then you are getting maximum intensity. There you are having I max is equal to root of I1 plus root I2 whole square. Then for phi is equal to pi, 3 pi, 5 pi, that is odd multiple of pi, there you are getting root of I1 minus I2 whole square. Which means whenever the phase difference between the waves superposing is 0, 2 pi, 4 pi, then constructive superposition happens, the intensity will become maximum. And where phi is equal to pi, 3 pi, that is odd multiple of pi, then you are getting minimum intensity. So that is the first concept in the superposition of waves, that is superposition principle, and based on superposition principle, where you are getting maximum intensity and where you are getting minimum intensity. Then depending upon the superposition principle of waves, we can have interference of sound waves. And when 2 sound waves of nearly equal frequencies are superposing, what will happen? Beats are formed. And we have defined some conditions for sound waves to be interface. So interference between two sound waves and necessary conditions are there. Phase difference between the waves must be remain constant. Then the amplitude of the wave, sound wave should be nearly equal. Then the displacement produced by the two waves should be along the same straight line. These are the conditions for getting sound waves superposed. And interference of sound leads to the formation of beats. And for beat formation also there should be some condition. That means amplitude nearly equal and frequencies are also nearly matching. That means very less difference in frequencies for the sound waves which are superposing, then only we are getting a beat formation. And what is a beat? When two sound waves of nearly equal frequencies are superposing, then alternate waxing and waning of amplitude occurs. That means intensity will become alternatively high and low, and one waxing and waning is called one beat. And as the beat formation, these beats are getting repeated. And again, using the superposition principle, we have formulated the beat amplitude. So again, y is equal to a sin omega 1t minus kx and y2 is equal to a sin omega 2t minus kx, where omega 1 and omega 2 are two nearly different frequencies. At x equal to 0, you are having the condition y1 and y2, then the resultant amplitude will be, resultant displacement will be y is equal to y1 plus y2. So a sin 2 pi f1t plus a sin 2 pi f2t. There you are making use sin a plus sin b. Then trigonometric identity you can use, and you are getting finally as 2a cos pi f1 minus f2t multiplied by sin pi into f1 plus f2t. So you are taking 2a cos pi f1 minus f2t as the common amplitude. So that will become y is equal to a sin pi f1 plus f2 into t. See, there you are taking the frequency difference term as the amplitude. Then only you can define how the amplitude of the resultant wave varies according to the frequency difference. Okay, so the difference of frequency we have already defined for the definition for beat formation. So again, for maximum amplitude, cos phi into f1 minus f2t should be plus or minus 1. For that, pi into f1 minus f2t should be k pi, where k is equal to 0, 1, 2, etc. So t is equal to k by f1 minus f2. So the conditions which are satisfying k equal to t is equal to k by f1 minus f2, where k is equal to 0, 1, 2, 3, etc. So when k is equal to 0, t is equal to 0, k equal to 1, t1 is equal to 1 by f1 minus f2. So all these instances we are getting maximum amplitude, that waxing of amplitudes are getting. And for a should be minimum, cos pi into f1 minus f2t is equal to 0. For that the condition is t is equal, pi into f1 minus f2t is equal to k pi by 2, where t is equal to k divided by 2 into f1 minus f2, where k is equal to 1, 2, 3, 4, etc. Remember, for maximum k varies from 0 to n, and for minimum k varies from 1 to n. Okay, so the t is equal to 0, 1 by n1 f1 minus f2, 2 by f1 minus f2, and 3 by f1 minus f2. All those points are maximum intensity, and t is equal to 1 by 2 into f1 minus f2, 3 by 2 into f1 minus f2, and 5 by 2 into f1 minus f2. All these points are for minimum amplitude. Okay, so that means when here k should be odd number, what happens when they are getting even number? That results in maximum amplitude. So suppose we are taking 2, then that will become 2 by 2 will become 1, so that will become 1 by f1 minus f2. 1 by f1 minus f2 is the condition for maximum. So for minimum, pi k should be an odd number. If it is even number, that results in the, or that merges with the condition for maximum intensity. So that is the beat formation. So we are having 4 conditions for hearing the beats. condition for hearing the beats is the two superposed sound waves producing the beats must be have frequency in the audible range. Both the sound waves are having the audible range. Audible range you are having 20 hertz to 20 kilohertz. Then the two waves should have very small difference in their frequencies. Then the difference should not be greater than 10. Then the amplitude of the wave should be preferably equal so that the maximum and minimum intensities of the sound produced in the beats can be distinctly heard. So these are the conditions for beat formation. Okay, so that is the first chapter, superposition of waves and beat formation. And in the second chapter, the superposition of waves, that means we are going to the bounded medium, and the bounded medium we define the medium which is well separated from its surroundings. So two types of boundaries are possible, that are soft boundary, that is rigid boundary, and soft boundary. So whenever the reflection is happening from a rigid boundary, there is a 180-degree phase difference between the incident wave and reflected wave. And whenever there is a reflection from soft boundary, incident wave and reflected wave are in phase. So when a incident wave reflected from a bounded medium, and both the incident wave and reflected wave are present in the same medium itself, then they superpose, and when they superpose, we will get a standing wave pattern. We are getting standing wave pattern. So in standing wave patterns, we are having zero amplitude points and high amplitude points. And zero amplitude points are called nodes, and high amplitude points are called antinodes. All these we have already discussed. So we can go for the condition, or how you can represent graphically the stationary wave formed due to reflection of a progressive wave. Okay, that is superposition of waves from a progressive wave. So, graphically, how you can represent a stationary wave formed in a bounded medium. That bounded medium is with a free surface, that is open end. So I already told you, from an open end or a free surface, the reflection happens. The incident wave and reflected wave are in phase. So you can graphically represent, on the right hand side you can see the graphical representation of the standing wave generated from a free surface. So left hand side you can see two incident, first the time duration is there, then the second column is incident wave and the third column is reflected wave. So the general equation is y is equal to a sin 2 pi by lambda Vt minus x for incident, y is equal to a sin 2 pi by lambda Vt plus x for the reflected wave. So at t is equal to 0, when you are applying t equal to 0 there in that equation, you can find y is equal to minus a sin 2 pi by lambda into x, and reflected wave will be plus a sin 2 pi by lambda into x. So they are acting in the opposite direction. Nothing is there. You can have our incident wave and reflected wave. I already given you the diagram for incident wave and reflected wave from a open boundary, that is open end or a free surface. So there you just take the points there at t equal to 0, t equal to t by 4, t equal to t by 2, and 3t by 4 and t. There you can find at t equal to 0, both the waves are acting in the opposite direction. At t by 4, both are acting in the same direction. At t by 2, they are acting in the opposite direction. 3t by 4, they are acting in the same direction. And at t, they are acting in the opposite direction again. Which means at t equal to 0, the graphical representation is like that only. The points n1, n2, at t equal to 0, you can have the points for nodes and antinodes. And at t equal to t, at t equal to 0, you can find the dotted lines are reflected wave. The other wave is that means the another dark line is the incident wave, then that higher amplitude wave should be the our resultant wave. So here at t is equal to t4, where you are getting the nodes and where you are getting the antinodes, it is represented there. That is according to the conditions where the waves are in phase and waves are out of phase. At t equal to 0 they are out of phase, at t equal to t by 4 they are in phase, at t equal to t by 2 they are again in out of phase, 3t by 4 again in the same phase, and t they are in out of phase. So that are the conditions given there, and where you are getting the nodes and where you are getting the antinodes that are provided there when they are superposing a wave, progressive wave is superposing when it is reflected from a soft boundary. Okay, and similarly we can see the reflection from a rigid surface also. See, when you are comparing these two, you can find the difference there. See, when rigid surface reflection is happening from rigid surface, at t equal to 0 they are in phase, at t by 4 they are in opposite phase, at t by 2 again in phase, and 3t by 2 opposite phase, and t they are again in phase. As I already told you, you just compare the reflection incident wave and reflected wave in both the cases. In the diagram it is clearly given in the during the class time. I have given that difference of incident wave and reflected wave in both the cases. So you compare that, from there you can find at t equal to 0 in from the rigid surface, at t equal to 0 they are in phase, at t by 4 they are in opposite, t by 2 again incident in phase, 3t by 4 opposite, and again t it is in phase. So that are the graphical representation. That is only for knowing how the standing waves are generated at different intensities and different intervals. Okay, so here our focus is the air column vibrations. Air column vibrations that we have already seen in an open organ pipe and a closed organ pipe. See, in an open organ pipe means both the ends are open. In closed end pipe means one end is closed. And in both the cases, we can find, in this case, what we have to do is you have to represent the incident wave, you have to represent the reflected wave. Since it is a closed end, there is a pi difference, phase difference will be there. Then you have to find out the resultant wave y1 plus y2. From there you will get two terms, one is time dependent and other is time independent. So that time independent term you can take along with the amplitude. Then remember, all the closed ends are nodes and all the open ends are antinodes. So for that you have to consider the condition at x equal to 0 and x equal to L. And there you are getting according to lambda is equal to 4L divided by 2n minus 1 in the case of a closed end. Reflection happening from a closed end. That means one end closed organ pipe. So depending upon the number of n, value of n, you can have first mode of vibration, second mode of vibration, like that. That means first harmonics, second harmonics, third harmonics, like that. Frequencies we are saying harmonics, and the mode of vibration we are saying first mode, second mode, third mode. And the frequency of first mode is known as the fundamental frequency, and that is the first harmonics. And the frequency of second mode is known as the second harmonics, but first is, that is known as the first overtone. That is a multiple of fundamental frequency. Okay, and in both cases we are having at least 3 modes of vibration you have to represent in with the diagram also. That means 3 modes of vibration you have to represent with the diagram and find out its frequency, then the ratio between the frequencies. You can see that in closed organ pipe, the frequencies are, frequencies of the different modes are in the ratio 1:3:5. That means only odd multiple of fundamental frequencies are possible, and even overtones are, or even harmonics are not possible. And we have seen in the same for open organ pipe also. The difference is in open organ pipe, incident wave and reflected wave is in phase. There is no phase difference. Again, you have to follow the same pattern. You have to represent y1, y2, and then y1 plus y2 as y, time independent term in amplitude. Then conditions, both the ends are open, so both the ends should be antinodes. So you will get the equation as lambda is equal to 2L divided by n. Again, depending upon the value of n, you will find the different modes of vibration, corresponding frequencies, and the ratio of frequencies. Okay, then there we have defined end correction. End correction means, I already told you in the class, when the open ends are present at the antinodes, present with the antinodes are not actually at the or exactly at the open end. It is somewhat higher than the open. So a length of air column is little bit higher than our pipe length, organ pipe length. So that the difference is the end correction. So that is superposition waves from air column. Then we have the standing wave produced in string. That means stretched string. So that we have discussed in the last class, stretched string vibrations. And in stretched string vibrations, we can have our both the ends are fixed, and when either the wave is reflecting from either end, we can have reflection from a rigid boundary. So 180 degree phase difference will be there, and after that we can have again follow the same path, y1, y2, resultant y. Then there you are getting the resultant wave equation as, or the lambda equation is 2L divided by n. That is very similar to both end closed. Equation are very similar to both end closed organ pipe, that is 2L minus n. Then first mode, second mode, third mode you can make use, and there you are getting the frequencies are in the ratio 1:2:3:4. That means all the frequencies are possible there. So here all together in this concept of superposition, you have to focus superposition principle, then superposition of two waves with the intensity equations, then beat formation, condition for beat formation, then bounded medium, standing waves produced in air column, two different cases, one end closed pipe and both end open pipe, then standing waves produced in stretched strings. So these are the concepts present over there. You have to focus over there and revise it thoroughly, and we will meet with the next class we will meet with another chapter in the next class. Till then, bye.